So my talk today will kind of get you kind of up to speed on how blockchain works and some of the applications that you can do with it and so forth. So the thing you have to look at whenever you're approaching this is, what's the big problem? What's the overall problem that we're trying to solve? And essentially, it's really a problem of maintaining many copies of a database and keeping them all synchronized. And in a lot of companies, you have a scenario where you have like a master database server, and then you have a bunch of slaves and so forth. But what we're trying to build here is something where all the nodes are peers, and there is no one node or any special nodes that are configured to be masters. And essentially the way the system works is a transaction, rather than just going to the master, it really goes to like all of the nodes, and it could be received by different nodes at different times. And so the problem is making sure that all of the nodes apply the same set of transactions. So you'll often see it referred to in the literature as the database replication problem or the state machine replication problem. And the benefits of having this kind of a system is that you get a lot of redundancy. So you actually have a complete copy of your database at every node. And so if you have any outage of one or two nodes, you're not going to have an outage in your service. But it also provides the benefit of decentralized trust, because if those nodes are all managed by separate independent entities, then there's no one entity that could, like freeze your account or manipulate the data, because if the majority of them are honest, then the changes that the bad entity makes would only be to its own database. And so this is, one of the key features that we've, are starting to now value. So when you try to deal with this problem, the worst situation that you could have is that you get what's called a state partition. Essentially, imagine, two different transactions come in, but the transaction, one of them is seen by some of the nodes first, and the other transaction is seen by other nodes first. And if you used a very naive implementation and you said, well, as soon as I see a transaction, I'm just going to apply it to my database, then you could end up with some nodes applying one transaction and other nodes applying another transaction. And those two transactions are, say, conflicting, so that you really can't apply both of them at the same time, right? One says, set color to orange, and the other says set color to green. And so you can't really apply both of those transactions. You have to get the whole network to agree on which one of those transactions you're going to apply. So that's where you need a consensus algorithm to avoid getting into a state partition. Now, on top of that, you also have to deal with scenarios where you have nodes failing, and then nodes may rejoin. You could have nodes losing some network connectivity, or there could be network lag between nodes. And then you could also have a whole network partition where like a bunch of your nodes get disconnected. Like if you kind of picture, like say if Australia had just one internet pipe coming into it, and that pipe got severed, and suddenly Australia lost connection from the rest of the world. What happens to all the nodes in your network that are in Australia? So you have to think about all these different fault cases as you design these consensus algorithms. And not only that, but you also have to account for scenarios where some of the nodes can be like rogue nodes trying to, purposely misbehave, right? So especially when you want to have all these nodes be provided by different entities, some of those entities, they may be anonymous. You don't know who's running those nodes and what they're doing, on that node. So they could actually try to cause, problems for your network, and nodes can even collude. And it's proven that if you have like at least you should be able to handle up to like 1/3 of your nodes being bad nodes and trying to collude, and still be able to get consensus. So you need at least like 2/3 of the nodes to be honest. And like I said, the worst case scenario is that you have a state partition, and that could be caused by many different things. So it could be caused by the network getting severed. It could be caused by dishonest nodes, and it could even be caused sometimes by your own software, like you do a software upgrade, but some of your nodes didn't get upgraded properly or something like that, and that sometimes you hear about that kind of stuff in the Bitcoin world, where there can be a hard fork because some of the nodes don't agree with the transactions or the blocks that were produced by other nodes. And they could even be caused by a bad consensus algorithm if you don't design your consensus algorithm properly. So there's something in the literature referred to as the cap theorem, and it basically says that in the event of a partition, your network can only be designed to maintain consistency or to maintain availability. So basically, say you had, part of your network was cut off, like the scenario that I gave before where Australia was cut off from the rest of the world. Well, what happens to those nodes in Australia? So like the Bitcoin network is designed to maintain availability. So those nodes in Australia will keep crunching and processing transactions and creating blocks, but they won't know that they're cut off from the rest of the world, and people can still do transactions within that, but eventually they'll recognize when the network comes back up that, hey, we were severed, and now we have to maybe throw away the blocks that we thought we generated, and because the rest of the world actually has a more longer chain. The other thing that you could do is you could maintain consistency in your data, but you have to interrupt your service. And so Stellar is another project that's out there, and they've chosen to go that route. So what happens in Stellar is if you have a large percentage of your network cut off or has a fault, then the whole network just does not process any more transactions. So you submit a transaction and it comes back and says, I can't process it right now, try again later. So within consensus algorithms, basically there's two classes of consensus algorithms. One is what's known as classical consensus algorithms, and these have existed since the 1980s. People were actually talking about it even in the 70s, but the first paper that proposed one of these classical consensus algorithms was the Paxos paper. And then over time, people have refined that and developed what's referred to as practical Byzantine fault tolerance. If you ever use, Hyperledger, Hyperledger underneath is using PBFT as its consensus algorithm. And there's also some more variations of it which have been used with Tendermint, which is being used with Cosmos, and also the Stellar network has developed a variation of that. But these classical consensus algorithms, they're basically permissioned. Essentially, it means that you just can't join the network. I mean, it's not open to anybody to join. You have to be permissioned and allowed in. And every node in the network is given an ID and knows about every other node in the network. And so typically the sizes of these networks is kind of small, maybe ranging from about 10 to 100 nodes. But the nice thing is the consensus is very energy efficient. Now you have the other class of consensus algorithms which were introduced originally in Bitcoin, and they're referred to as Nakamoto consensus. Now the key feature of this is that it's open and permissionless. And so anybody can join that network. And the size of that network is pretty much unlimited. You can have, thousands and thousands of nodes in that network. And nobody has to assign you an ID to participate in that network. You just can come in, join the network at any time, leave at any time. However, the drawback of it is that the consensus is very expensive and requires using a lot of energy in order to be able to show that you've produced something that everybody can agree on. But it's become very popular, and Bitcoin, Ethereum, and a lot of the other projects out there that use a blockchain are using this Nakamoto consensus. And so, like I said, Bitcoin was the first place where this was introduced, and essentially you have a network of nodes that are competing to create blocks, and the blocks contain a set of transactions that are accepted by all of the other nodes in the network. And the transactions is where the actual, application layer comes in, right? Where you're actually like moving money, or in the case of Ethereum, you're making changes on a contract, things like that. So if you start thinking of a particular application, like let's say, you have a bank. What does a bank do? Basically, you can simplify it so that they're just keeping a big database, and the database has all these accounts, has customer information, has your balance, right? So it's really a fairly simple database. But a typical bank will just keep like one master database and then have lots of backups of that database. And the transactions that are submitted to the bank are used to then, make changes to that database. But you have to trust the bank to make sure that they're not making changes to things that, you don't really want changed. And you have to trust them to, not freeze your account and all those kind of things, like actually process your transactions, right, when you submit the transaction. So if you go to the next slide. So how would you take a bank application and put it on a blockchain? So essentially, on a blockchain, you still have accounts, but they're represented with addresses, and you don't have customer information. Blockchains don't care about who you are. And then you just have your balances or any other application data. And so that provides like pseudonymous accounts. And another nice feature is that you don't have a master database anymore, but instead you have a whole bunch of peers, and each one has a complete copy of the database, so you have a lot of redundancy, and there's very little chances of the service going down because the database is down. And you only have to trust the technology now. You don't have to trust the bank or some entity that's centralized. So like the Bitcoin network, you can think of as sort of providing you a service like a bank. You can transfer coins on the Bitcoin network. And so these green rectangles are basically transactions, and a client would submit one of these transactions into the network. It propagates around through what's called like a gossip protocol, gets to all the nodes. The nodes collect these transactions and try to put them into a block, and the block has to meet some requirements so that it'll be accepted by the rest of the other nodes. So now I'm going to get into some of the details of what happens inside the block. Or actually, so the database that each node is keeping is really a long chain of blocks, and then from this you can infer the state of all the accounts and their balances. But really you're just keeping track of all the transactions. Now within a Bitcoin node, what the node is doing is trying to build the next block, and it does that by taking all these transactions that are being propagated. So transaction might say, move some coins from account A to account X and so forth. You actually have to validate the accounts first to make sure that the funds are there to be able to move. And you take the valid transactions, you put them together, but then you add your own transaction at the top that says, pay me for finding this block. And then you have to also add what's called a nonce, and that's like a random number, which when you take the hash of the whole block will meet some threshold, and then that is what allows the other nodes to say this is a legitimate block. And then once you've produced that block, then that gets added to the chain of the next block. Go ahead.
Is adding that extra, I guess, end to the hash, is that for like user authentication? Or what is that exactly for?
Oh, so the nonce?
Yeah.
No, that's only just to be able to change the nonce so that you can continue changing like what the hash comes out to be. So I'll get into that a little bit more on the next slide. Yeah, so that nonce is just a random number. And so you have all these transactions, and the transactions are grouped into a block, but then you have a random number. But you also have a pointer to the previous block in there. And that's what ends up making this a chain, because each block is pointing back to the previous block. If you go to...
Just to add, that nonce helps to make unique, helps that transaction be unique.
Yeah, makes that whole block unique and helps you to be able to produce a hash for that block that meets the current requirement for what we want the block hash to be.
So there's nothing keeping track of the random numbers being generated, right?
No, those are completely random.
Okay.
Yep. Go to the next one. So essentially, if you take that whole block of transactions, you add a random number to it, you take the hash of it, so the hash is essentially like, generates a checksum. You check to see if that meets certain threshold. If it doesn't, then you just pick another random number, add it to this block, and then go through that cycle again until you finally do find one that meets the threshold. And once it does, then you can put that block out onto the network, and other nodes that receive that block can validate it very quickly, because they just have to do one hash of the whole block that you sent, and also check that it met the threshold requirement, and then they have reason to accept it.
What is the normal threshold that's used?
So that threshold actually varies, and the threshold is varied by looking at the rate at which the blocks were produced over like the last 2 weeks in the case of Bitcoin. And you're trying to get it so that you have like one block produced every 10 minutes. So if you're producing blocks faster than every 10 minutes on average, then the difficulty increases. And if it's getting slower, then the difficulty gets reduced. And that difficulty is getting like crazy, crazy high right now. I don't remember exactly what the difficulty is, but the amount of hashing that you have to do in order to meet that difficulty is kind of like so many exahash per second kind of number of hashes that you have to try in order to be able to find something in 10 minutes, right? So, yeah, it's the difficulty is getting pretty high. So, stepping back, now you kind of have an idea of what a blockchain is and how, the network works to produce blocks and so forth. Now, how does this overall blockchain technology, what can we use it for? And how should you think about it? Essentially, any place where you have a third party that you need to trust in order to provide your application, it's a candidate to be replaced by blockchain technology. There's a guy named David Johnston, I think back in like 2012 or 2013, he said, everything that can be decentralized will be decentralized. And so it's kind of like Johnston's law. And we're probably going to go more and more towards that. So third parties that provide trust will eventually be probably replaced by blockchains. And you can think of, that blockchain is just sort of like the back-end infrastructure. Like right now, we have many, many companies out there that provide some sort of a back-end infrastructure, right? Like take the case of Uber, for example. Essentially, Uber is a back-end with a mobile app client. Now, for providing that back-end and client, they're a third party between the person who wants the ride and the person who can give the ride, and they're taking a cut out of that. So with blockchain technology, you can have a bunch of individuals like yourselves downloading some software and running it on a VPS server or something like that, and all your nodes would talk to each other and provide that back end. So we don't need a company to provide the back end. You guys can provide the back end. And somebody's written the software to allow that to happen. And you will get paid in some coins on that platform in order to provide that service, because you're going to have to pay for your VPS server. So with the coins that you received, you'll be able to afford running the server. And then the person that wants the ride, they'll actually have to acquire those coins in order to pay for the ride. So that's usually how these blockchain applications work. And essentially inside the cloud, like I said, there's a lot of nodes that are interconnected and have a database that they're each have a copy of. And nodes are rewarded for providing the service. And even if there's failure and collusion and things like that, the network will still continue to survive as long as you have, 2/3 of your nodes are honest nodes. And so essentially we're replacing trusted third parties with sort of this blockchain cloud service. And it's a huge industry, and I think there's like trillions of dollars of transactions and commissions that are being taken out of the economy by these third parties for providing that service. And in the future, that's going to go to platforms that are providing these services using blockchain. So like different applications, we already talked about like how to do like a bank transfer scenario. But typically right now with banks, if you want to transfer money from bank A to bank B, it takes 3 days. I mean, there's no reason for that, right? I mean, you know how long it takes to text a message. It doesn't take 3 days. Sending money is not any harder than sending a text, okay? And so, banks have been just sitting on their butts for all these years, and now, blockchain is gonna like come and say, we're gonna replace you if you don't do something. So they're gonna have to lower their fees. They're gonna have to, get on the ball in this world of like, 3 days to transfer money is going to be gone in a few years. Also, there's, like escrow services. I don't know if any of you guys have bought a house before, but if you ever bought a house, it's a kind of a painful experience. So there's these companies in the middle, they're called escrow companies or title companies, and basically they provide the service of, taking the keys from the seller and taking the funds from the buyer, and then holding both of those for a little while and then doing the swap. And for doing that, they collect like thousands of dollars in fees. Eventually your house titles will be on a blockchain, your car titles will be on a blockchain, and if I wanted to buy your car, I could just transfer you the coins and you could transfer me the title. So it's going to be that easy, and you don't need like these escrow services. And there's even a feature now in blockchains called atomic cross-chain transactions, or atomic cross-chain swap. So we don't even have to worry about like, should I send you the money first or should you send me the title first? It could be done in such a way that it's like, I can put up the transaction to send you the money, but it won't go through until you've sent me the title. And so we don't even have to trust each other on that. Another example is crowdfunding. You guys probably all seen Kickstarter and Indiegogo and those type of sites. Essentially, what are they doing? They're basically a middleman, essentially providing the service of allowing people to, contribute to a project. But basically, all you're doing is if the amount of contributions to that project exceeds a certain amount, then the money goes to the person who started the project. Otherwise, it goes back to the people who sent the contributions. You could create a smart contract on Ethereum to do that, and so you could run your own, crowdfunding thing with just an Ethereum contract. And there's probably already contracts that people wrote up and put up there, so you could just like copy that and just set it up, and you don't have to pay a 10% fee to somebody in the middle. And you get to keep all of the contributions. So other applications, decentralized DNS, domain name registration. If you guys ever registered a domain name, that's also third party holding it. In fact, Ethereum already has a Ethereum name service out there. Just Google that. You can bid on domains and register them, and they're held on the Ethereum network. There's other projects like OpenBazaar, which are basically like a marketplace similar to like eBay. There's a service called Lazos. It's kind of like a ride-sharing service similar to Uber. Steemit. Steemit is somewhat like Reddit. So, lots of, social network type sites will be possible, but right now, they're not that practical to do right now because the networks are not very fast yet. But once, we increase the speeds of the networks, then you're going to see more and more, social networking type of sites become possible. There's also a project called Storage. I think there's a few more, Scicoin and Filecoin. They're basically providing like disk space that you can rent out, or you could, rent if you needed disk space. Go ahead.
So these are all applications that are using blockchain. I guess the protocol of confirming blocks to provide whatever service they're doing. Is that what's happening?
Yeah, so the protocol is, for most of these, they're using like the Nakamoto consensus protocol, which is, like creating all these blocks.
And that's why you said I guess the the usability depends on the network speed? Because at the end of the day, they're still always confirming a block.
Yeah, exactly. Right. So depends on how fast you can get those transactions processed, right? Or how many transactions can you process. So that's going to be your limitations in terms of like what applications you can do with it. And Ethereum basically, it's like a decentralized cloud computer, right? So, you can just write up some code, put it up there in the cloud, and you didn't have to rent any server or hardware or anything like that to run that code. And people can access it from all over the world through a client that you created, right? So that's pretty cool. And even further in the future, you're going to have essentially anywhere where you need to prove ownership in order to do transfers. You can think of it as a place where you're going to need blockchain. Identity, right now we're in a world where our identities are sort of issued by governments, but in the future, you're going to have identities that are like earned based on your reputation and so forth. And those kind of identities are actually going to be harder to fake than, an identity, given by this piece of plastic, right? And we're going to look back to this era and laugh about it and say, oh my God, like people used to just use this as your identity? Like, you mean I couldn't just like go to a blockchain and check your identity? That kind of stuff. So, because if you think about it, we really can't check each other's identity, seriously, right? Like, if I ask you, like, hey, what's your name? And you say, John, and I say, okay, prove it, and you pull out, this piece of plastic, and it has a picture of you and says, John, does that really mean that really, should I believe that? I mean, how do I know you didn't just make that up, right? So what if instead you pulled out your phone and you showed me a QR code, and I scanned your QR code, and then my phone goes to the blockchain and then, pulls the record from the blockchain and then is able to check it, right? So that is more authentic, right? You couldn't have faked that. And so, we're going to have those type of identities, and also places where, you don't want records to be tampered with. Like I said, like titles, assets, any kind of things like diamonds or, big valuable things are all going to be digitized and put on blockchains. Eventually you're going to have stocks. Also, every company's shares are going to be turned into assets and put on blockchains. Healthcare patient records, those are all going to become like owned by the patient, and you don't have to worry about like, every hospital or doctor having to maintain their own copy of patient data. That data will actually be owned by you, and wherever you go, your latest version of your record will be available. And then also for like single sign-on to like corporate networks and things like that will also be possible. I'm part of team of the Shardis team, and what we're doing is trying to build the underlying technology to make global scale decentralized applications possible. By global scale, we're actually thinking in terms of like billions of daily active users, right? Like suppose you really had one of these decentralized applications and everybody in the world wanted to use that. Could we really handle like 7 billion people using the same network? Well, that's the kind of global scale that we're trying to shoot for. And to do that, we're using sharding, which is a technology that's been used in the database world for a long time, but we're applying that now to the blockchain and doing it at the core level so that it's not like a layered technology, but rather designed into the distributed ledger. And that's what gives it that scalability. So essentially, as you add more nodes to our network, we are able to provide more and more transaction throughput. And most of the current blockchain systems they're limited in terms of how many transactions per second they can process, and adding more nodes doesn't really help those networks. So that's one of the drawbacks, but hey, at least we have trustless systems, right? So we crossed that hurdle, but there's still a lot more work that needs to be done to really make these systems a lot more faster. And then we're using a consensus algorithm. So we're trying to keep our system permissionless while it's still, very fast. And also we're trying to keep the consensus very energy efficient. So it's not expensive for you to do your transactions on that network. And then the validators, nodes that run that network, they'll be paid on a daily basis. Unlike like in Bitcoin and things like that, you're paid like suddenly. And so that causes people to want to join mining pools and, in order to have a more steady income. But with our networks, the nodes would actually be paid on a steady, guaranteed basis. And we're basically not doing any kind of ICO or anything like that, and we don't plan to. But we are giving our tokens to people who are helping to develop the project or our software, helping to promote it or do anything else for the project. You can earn the tokens, and once you receive the tokens, since they're ERC20 tokens, you can go trade them on the Bancor network or Ether Delta or any of these decentralized networks. And so Shardus is essentially the technology, and on top of that, you'll be able to build whatever applications you want. And so one of the first applications that we plan to build with it is just a payment network where you can, transfer money. So you can learn more about it at shardus.com. And if, we're always looking for talented developers, so if you want to reach out to me, you can email me also at omar@shardus.com. So thanks. I think that's all I have.
So you had permissionless and then you had consensus, correct? Like that was two of your bullet points there, but I thought permissionless was something that was with the other.
Yeah, that's a good question. So like earlier on when I showed the slide for the two basic classes of consensus algorithm, you have the classical consensus algorithms, which are not permissionless, but they're efficient in terms of consensus. But then you have the Nakamoto consensus algorithms, which are permissionless, but it's pretty expensive. So Shardus is actually, because we're doing sharding, we do consensus at each shard, and within the shard, the nodes know about the other nodes that are participating in that consensus. But across the whole network, it's still permissionless in the sense that a node can join the network and leave the network at any time. So
is sharding just a condensed story of the previous network that existed?
okay.
Is sharding more like, I'm trying to understand what sharding really is, what you mean by that. So is it just new hardware that's allowing to do something, or?
Okay, so essentially what sharding is when you have any kind of like data or compute that you want to distribute and have it done in parallel, you can take the resources that you have available and group them into shards.
Okay.
So, for example,
Like RAID?
yeah, exactly, yeah, like RAID, right? Yeah, that's a great example, like with disks, right? So if you want to have multiple disks holding like different pieces of hardware, you can distribute, some of your content to different disks.
Right. And since it's blockchain still, there's still like a public and private key within those shards that are individualized, and is that what talks to the network?
Well, you still need the public and private key to on your transactions to make changes to the data.
Gotcha.
Yeah. Yep.
Thanks a lot.
All right. Any other questions? All right, well, thanks a lot, guys, for coming out, and wish you guys best of luck in the competition.